Questions about anything from last time, about anything?
Wait, is this a definition for this connected?
Yeah, I'm going to talk more about this in a second. Today we're finally going to mention the objects we're going to study in this course, which are analytic functions on domains, which are, domain is a word for connected open set in the complex plane. And I mentioned earlier in the semester the concept of being path connected when I was showing that if a function has zero derivative, then it's got to be constant. And that's true when the set underlying open set is connected or path connected, which is the most natural version of being connected. It means the thing is all one blob, and you've given any 2 points in the region, I can join them by a curve. And here we're going to take a Math 530 definition to be piecewise C1 curve, because of course we like to integrate along that kind of curve. It's a remark, though, that topology in more general spaces would say that the curve gamma connecting those 2 points gamma connecting A to B in omega needs to be merely continuous. And it's a simple in R2. Whenever you have a continuous curve connecting two, I showed you how you could get a piecewise C1. You take chords. So this is equivalent. This is equivalent in open sets. In R2. Because whenever you can connect 2 points, A to B, inside a region, so here's A, here's B, and we're connecting it by a gamma, well then it's a simple matter to get a piecewise C1 curve. You just take chords. Etc. So you can get a piecewise C1 curve that does the job. Questions about that? Okay. So the second definition of connected, which is the more formal topological concept, has to do with, I'm calling that one definition number 2. An open set is called connected if, when you can write it as a union of 2 other open sets which are disjoint. Well, there's only one way to do that. One of those open sets has to be all of omega, and the other has to be empty. Sorry, what's happening here? What the heck? Okay. Then one of the u's equals omega, and the other is empty. Okay. Well, it's an easy fact that these two definitions are equivalent for open sets. Definition 1 and 2 are equivalent for open sets. So for us, the most natural and easy concept is path connected for open sets in C. For non-open, I mean, if you have, I can show you. It's a topology thing. If you take Math 571, there'll be examples where these two things are different, and the sets are more wild and crazy, and they certainly aren't open. They're there's the classic example. I don't think I'll do it. It's more of a topological fact. Questions about that? So look that up in a topology book probably for the examples. What the heck, I'll give the example. So this fact is not true for wilder and crazy examples. So this is from a topology class. Topology example. Let's see, what's the famous example? I take, let's take a dotted line like this. Another dotted line. Here I know what to do. Now they're parallel. And now I'll put, this is the real line. And now I'm going to graph sine 1 over t. So here's the t direction. And I'm going to graph sine 1 over t, which wiggles along. And it starts wiggling like crazy, etc. So that's the graph of sine 1 over, make it 1 over t squared if you like, or 1 over t is fine. I won't think about it on the negative real axis. And then I toss in this red line. And then when you're talking about connected and talking about open sets, this is a set. It's a closed set. And when you're talking about open sets in the definition of connected, they need to be relatively open in the relative topology. So that thing has a relative topology in which you can talk about open subsets. Anyway, that set, graph plus the graph union, the red line, is connected, but obviously not path connected, because pick a point on the blue curve and ask yourself how you'd connect it to a spot on the red line by a continuous curve. Of course, the curve would have to follow the blue thing and go totally ape, and nowhere would certainly would not be continuous. So union red line is connected, but definitely not path connected. And path connected with the concept of a continuous curve connecting, but not path connected. Okay, but in our setting of open sets, we don't have to worry about wild and crazy things like that. Okay, so today I'm going to talk about zeros and analytic function and do the famous theorem called the identity theorem. And we've kind of come up with a version of the identity theorem that I described at the end of last hour. And so I need a lemma for today. It's a power series fact that if f is analytic on a disk, on a disk of radius r about z naught, and f has a 0 at the center, then either f is identically 0, on the disk of radius r about z naught, or the 0 is isolated. It can be shrunk down on a little disk of radius epsilon, so that's the only 0. Is an isolated 0. Okay, and you remember the way I did that. To remember the proof from last time, I'll sketch it quickly. I would write f as the power series, and let's say all those derivatives vanish at the origin. All of its derivatives vanish at z naught. Well, then, of course, its Taylor series would be the 0 series, and it would be identically 0. So, if it's not identically 0, there would be a first coefficient an that would have to be non-zero. So that's the first non-zero Taylor coefficient. And that would be times z minus z naught to the n plus, et cetera, et cetera, et cetera. And what I did last time is realize, I can pull out that z minus z naught to the n. And what's left is a power series. And that power series converges for exactly the same z as the power series for f. And so it has the same radius of convergence. And I call that capital F of z. And because f of z at the center is an, which is not 0, that means I can find a disk that makes it not 0 on the whole epsilon neighbor, or say delta neighborhood. So the important thing here was that f of z naught is an, and that's unequal to 0. Okay, and there's a word for this kind of function. That's an nth order 0 at 0. So the definition, f has a 0 of order or multiplicity, if you prefer, n at z naught. If all the derivatives up to order n are 0, except the nth one is the first one that's not 0. So a 0th order 0 would just mean the function has a 0 and the first derivative is not 0. So for example, z squared would have a second order 0. Questions about that definition? Well, now, that's all we need to prove the famous theorem that's the main subject of today, namely the identity theorem. Let's suppose f is analytic on a domain omega. Let's let z sub f be the set of zeros of f. So that would be the set of z such that z is in omega. So z in omega such that f of z equals 0. So it's the 0 set. Then the fact is either f is identically 0, which means that the whole omega is the 0 set. Either A f is identically 0, or B, the zero set has no limit point in omega. Has no limit point. The zeros can't pile up. Has no limit points in omega. So in is an important word here. Zeros can pile up at the boundary, but they can't pile up at a point in omega. And the path-connected definition of domain is going to make this a very straightforward thing to do. The other definition, number 2, would make it a little more challenging. And I get tongue-tied every time I try to do it that way. So I much prefer the path-connected definition. Questions about anything? Yeah.
So could f be 0 on the entire boundary?
Oh, you like to think about things like that? That's a really interesting question. Of course, it couldn't be continuous up to the boundary if that was the case. So it'd have to go totally bonkers. And yes, it is possible to, if you can, there's a theorem called the Weierstrass theorem that we can prescribe the zeros of an analytic function. And we could have sequences going out to the boundary of zeros that accumulate at every point on the boundary. Of course, the function would go totally bonkers, ape, as it approaches the boundary. But yes, it's possible to come up with pathological examples like that. I told you there'd be no pathology in complex analysis, but I guess maybe if you really work at it, you can find some. Okay, so the proof is going to be fun. Let's suppose the zero set has a limit point. Suppose Z naught in omega, that's important, so I'll underline that, epsilon, is a limit point. By the way, there's other words for limit point. Accumulation point is the same thing. There's a limit point of ZF. Well, omega is open. Let's see, what does it mean to be a limit point? Meaning there exists a sequence Zn n equal 1 to infinity of points in the set with the Zn's would all have to be unequal to the Z naught. And the limit, as n goes to infinity, of Zn is equal to Z naught. Something to note is that f is continuous. I mean, f analytic implies f continuous. So f of Z naught equals the limit as n goes to infinity of f of Zn. Those are zeros, so of course that's equal to 0. So the limit point of the zero set would also have to be a 0 in this setting. Well, the fact that omega is open means that we can find a disk. There exists an r bigger than 0 such that the disk of radius r about Z naught is contained in omega. And of course, that's the disk I'm going to apply my lemma on. My lemma, that would not be an isolated 0. So my lemma implies that f is identically 0 on that disk. So I've got an analytic function that vanishes on a disk. That's going to turn out to imply that it has to be identically 0 on all of omega. Analytic functions can't do that. So it's not like continuous functions that you could make them be 0 for a while and then start making them do something. If they're 0 in a little segment, they got to be 0 everywhere. That's not true about continuous functions or even real differentiable functions. So if it's 0, lemma implies it's 0 on our disk. Okay, now we're going to use the path connected concept. So my claim is f is identically 0 on omega. And I think I'll do a picture proof. Let's take our z naught here, and let's take our omega. It's connected. It's path connected, which is the same as connected. It's an open set, and so it could have holes. So there's our omega. Pick an old point here in omega, W naught. Since this is path connected, I can join these by a piecewise C1 curve. So there's a piecewise C1 curve. So pick any old Z naught, W naught in omega, get a curve, piecewise C1 curve, gamma, joining them. Z naught to W naught in omega, which means the trace of gamma is contained in omega. Okay. Well, then you think about what we might do. We've got this disk here of radius little r, and f is identically 0. So you think that you look at that and realize, aha, that function f will be identically 0 in the beginning of that curve in there. And so there'll be a segment where it's identically 0. Okay. So let's suppose our gamma's piecewise C1. And let's suppose it's parametrized by z of t. Question?
Are you going to take like the radius and inverse of each point on the curve and then take like an open coupler or something?
Well, that's what you would do if I locked you in a room and said, how are you going to show that the value at W naught's the same? Well, you draw that disk and say, aha, these things pile up right here, so I can make this the next disk and do the same thing. And then I could do that again at the edge of that disk, and I could get like a caterpillar chain of disks. And the question is, well, will you make it to the end if you do that? What if the disks, like Zeno's paradox, start getting smaller and smaller for some reason, and you can't, you just can't get past a certain point? The question is, can you get past every point and make it all the way to a W naught? The answer is going to be yes, but that's why mathematicians invented these fancy concepts of connectivity to avoid thinking in those terms. But that's how you would feel about it, and sometimes in a more elementary class about complex analysis, that's what I just do. You can do it with your bare hands there and see, oh yeah, I'm going to make it. But I'm going to show you what this trick in math is to get around that kind of thinking. let's let capital T equal the sup of all tau such that f of z of t is identically equal to 0 for a less than or equal to t less than tau. It's clear that t is bigger than a because of that first little disk. So on that pink, f is identically equal to 0 on that pink disk. Okay, so from that picture, we see that t is bigger than a. I claim that t is equal to b. It goes all the way to the other end. Capital T is I can go all the way to the other end. Okay. And the y is simple. It's easy to see that that t is not an isolated 0. Z of t is not an isolated 0. Because I'm coming at it from the left, there'd be zeros, and they would pile up at the end. Okay, and therefore therefore I can now do my same old routine. So as at z naught, we get a radius such that f is identically 0 on the disk of radius rho about z of t, which is contained on omega. And so let's see, if I was going back to my picture, I'd get to my W naught here, and I'd get to my Z of t. It would be 0 on this coming into it, and then I kind of picked a bad spot because I have to make my rho really small. That red dot is my Z of t. It's 0 coming into that red dot, and that'd be and now I just see that it's identically 0 on that disk. That means I can go farther. It means that t is not the sup. So this is the contradiction. That's my symbol for contradiction. T is not the sup. Not the supremum. I can make it. Oh, let's see. When could I not make it bigger? That I couldn't. It's not the supremum. If it was, that would be true if t is less than b. But of course, if I made it all the way to b, I'd be happy. So t is equal to b. Okay, so where's my actual contradiction? My actual contradiction would be after I made that observation. Questions about that? That's kind of a fun argument. Very little work. The alternate proof that I always fumble around with is to use the other definition. Use omega equals open set 1 union open set 2 open, and disjoint. With, let's see, it's hard to figure out what they should be. With, you might think U1 should be the zeros of F, and you'd get bogged down and mess that up. You couldn't make it work. U1 is equal to the set of Z, well, let's call it W in omega, W in omega, such that W is a limit point. Of Z sub F. Okay. And then you have to show that U is both open and its complement is open. So U2 would be omega minus U1. And then the hard thing to do would be to show, well, it's not hard, but you have to think about it. Use the lemma to show that U1 and U2 are both open. And then the fact that U1 would be either the whole thing or nothing gives you the result in the end. Anyway, I'm not going to do it that way this time. Questions about anything? That's a fun thing to sit down and do, to make sure you understand that lemma and its consequences. Well, this has a great philosophical meaning for complex analysis. So, for example, something we now can see is that there's only one way to extend the complex exponential to the complex plane. So e to the z is the unique extension of the real exponential. So e to the x from r to c. Let's see, how would you see that? If I had another one, I'd look at e to the z minus, say the other one's f of z. E to the z minus f of z would be 0 along the real line. And every point in the real line is a limit point of the real line. So the deal here is, if I look at the real line, every point in R is a limit point. In Z. So give me a point. I could easily find points that pile up there. Just add 1 over n. They pile up there. Okay, so if I had another extension of it, call it f of z, e to the z minus f of z would be 0 on a set with limit point, so it would have to be identically 0 on the whole complex plane, which is connected, open. So that means there would be agree. So in fact, that leads to a corollary. If two functions agree on a set with a limit point, then they have to be the same function. So corollary, if two analytic functions on a domain omega agree on a set with a limit point in omega, then they agree, period. Then they're the same. On omega. So that means, once again, that you can't go around deforming analytic functions. They're completely determined by their values on a set with a limit point. A fun consequence of that is that all the trig identities you ever learned are true for complex angles. So consequence, every trig identity you ever learned holds for complex angles. Trig identities hold for complex valued angles. So, for example, sine 2 theta is 2 cosine theta sine theta. That holds for along the real line. You let theta go complex and realize, okay, there's an analytic function Yeah, if I subtracted it, I get an analytic function that's 0 along the real line. And so, of course, I'm using the definition of sine of z is e to the iz minus e to the minus iz over 2I. That agrees with the sine function on the real axis, so it's the only way to extend sine to the complex plane. This is cosine plus e to the minus iz over 2, etc. And the tangent function would be sine over cosine. So this thing holds for theta in the complex plane. And of course, if you have a trig identity like sine alpha plus beta equals, let's see, I multiply e to the I theta times e to the I alpha times e to the I beta and take the real and imaginary parts to remember this every time. And I get, oops, I don't get that. I get sine beta plus sine alpha cosine beta. Okay, so this is, this for real values. First, I'd hold beta constant and I let alpha go complex. I'd get a correct formula for alpha being z in the whole complex plane. Then I'd hold the z fixed and let beta go complex. So do it one at a time. So first, you'd let alpha equal z, and second, you'd let beta equal w. And you'd see that it holds for complex. It's worth pointing out that the identity theorem is way false. I said there's lots of examples you could come up with, but it's way false for differentiable functions. It's easy to think of differentiable functions that are 0 on an interval, and they're just not 0 everywhere. And here's a more exotic example that I like. So it's way false R to R. And the classic example I like the best is you take a h of t and let's let it be 0. Let's see. Let's let it be 0 for t less than or equal to 0, and let it be sine 1 over t squared for t bigger than 0. So that wiggles like hell as you approach the origin. Oops. That's not what I want to do. Sorry, I'm going to fix this. That's not even continuous, so that's not going to be an example. I want it to wiggle like hell, but I'm going to squash it with a function that dies away very rapidly. E to the minus 1 over t squared dies away incredibly rapidly. So rapidly that that would go to 0. And not only that, but all the derivatives would go to 0. And in fact, you can show that that function is infinitely differentiable. So this thing is C infinity smooth on R. And the zeros, oh, let's see. Why don't I do this? I want the zeros to pile up. So this works for negative t too. So let's make that t unequal to 0. What am I saying? That's ridiculous. This is where I want to put the unequal to 0. It's equal to 0 at t equals 0. Okay. Wiggles like hell, but the wiggles get smaller and smaller as they go into the origin. And they get killed so fast by that e to the minus 1 over t squared that even the derivatives go to 0. And the zeros pile up at the origin, but it's not identically 0. But h is not identically 0. H is also the example of a C infinity function that doesn't have not equal to its Taylor series. So this is also a classic example also. H is unequal to its Taylor series. At t naught equals 0. So it's an infinitely differentiable function that's not given by a Taylor series. It's given by a Taylor series everywhere but 0, but not at 0. Let's see. Of course, you can... Let's see. Another remark. I can factor out finitely many zeros if I want to of an analytic function. So I'll put it in quotes. I can factor out finitely many zeros so let's see. When I did that, I would have f of z equals... I did it for 1. I'd pull out a z minus z1 to the m1. Then I'd have here, I'm going to erase it in a second, I'd have an f of z here, remember. Well, if there was other zeros, that capital F of z would vanish at the other zeros. And I could, one by one, I could pull them out. At least I could do finitely many that way. So then I'd pull out the next 0. And then I'd have a h of z here. And if f had more zeros, then this h would have zeros at those spots. And I could keep doing that. So I'd go dot, dot, dot. And I'd do it maybe n times and get sick of doing it. And finally, I'd have a g of z left here that doesn't vanish at those points. With g analytic on omega and non-zero at the z ends. That's something nice to know. So that means analytic functions behave like polynomials. I can factor out the zeros and be left with something that doesn't vanish at those spots. Of course, unlike polynomials, analytic functions can have infinitely many zeros. For example, sine 1 over z has zeros. Let's see, sine is 0 exactly at multiples of pi along the real line. So that would have at places where 1 over z equals n pi. Which would mean that z is 1 over n pi. And of course, so that has infinitely many zeros for one thing. And it looks like the zeros are piling up. Does that violate the identity theorem? They're piling up someplace. Why not?
Because it's not analytic at z equals 0.
Exactly. Yeah. So there's whenever I talk about analytic functions, there's an omega in the background. In this case, the omega, the open set where it would be analytic, would be the whole complex plane minus the origin. That's open. It's connected. So that's the domain where this function is analytic. That goes totally bonkers at z equals 0, and it's definitely not analytic there. It's not even continuous. And so it's okay for zeros to pile up at boundary points. Pile up at boundary points. Oh, yeah.
So if a function has finitely many zeros, then we can factor them out.
Yeah.
This is infinitely many zeros.
Yeah, so that's a fascinating subject. And if you start paging through Stein toward the end, or even toward 2 or 3 chapters ahead, a big topic in complex analysis is factoring functions and expanding them in like partial fractions. That's and those famous formulas about the Riemann zeta function, the gamma function, they have to do with exactly that. And Euler and all of the historical figures went totally ape thinking about those things. And they're beautiful formulas when you start playing games with them. Yeah, I wish I could think of one off the top of my head. There's a beautiful formula for sine of z squared, which will blow your mind, because it involves classic numbers like, kind of like e to the I pi is plus 1 equals 0 formula.
Could we write sine of 1 over z as an infinite product?
Well, let's see. You can write sine of z as an infinite product, so it would be a 1 over an infinite product. Anyway, yeah, page ahead in Stein, you'll see a whole bunch of formulas that are kind of hard to believe. Other questions about anything? So next subject is the maximum principle. I was going to try to squeeze in a lemma here at the end, but I think I'll start with that next time. Maximum principle is going to require a little calculus lemma, which I'll start with. Anyway, you should be reading along in Stein. I think we're in the middle of chapter 2 now. Homework 3 is due tomorrow night. And I'll respond to the questions I've been seeing on Piazza about one of the problems.